Welcome to the session on differentiation, differentiating sinx and cosx. The objectives for this session are to differentiate trigonometric functions. A curve has a constantly changing gradient or slope. It is possible to find the gradient of the curve at a point by finding the tangent at that point. The straight line that just touches the curve at a point is the tangent at that point. So we can say that the gradient of a curve at a point is the gradient of the tangent at that point. Let's take a look at an example to illustrate this. For the curve y equals x cubed minus 6x squared plus 11x minus 6, we will find the gradient of the curve by using a sketch. So here's a sketch of the curve. And here's the line at a particular point on the curve. The tangent to this curve has gradient 2 at 3, 0. Notice that it just touches the curve at this point. Bearing this example in mind, let's see if we can get something more precise regarding the tangent at a point on the curve. So consider first a continuous function f of x. We also consider some point c on the x-axis. This is sent to f of c on the y-axis. Now consider the value c plus h on the x-axis. This is sent to the value f of c plus h on the y-axis. Notice that the red dotted line denotes the gradient at the point C. It is clearly not going to be easy to find this gradient exactly from the graph. One way to find it is to consider the gradient of the line joining f of c to f of c plus h. And looking at the diagram, as B moves closer to A, the gradient of AB approaches the gradient of the tangent to the curve at A. The gradient of the line joining f of c to f of c plus h is change in y, as shown by the blue line indicated by an arrow, divided by change in x, which is equal to h. So as h gets closer and closer to 0, the gradient of the thick red line approaches the gradient of the line at C, as you can see. So we can write this as the derivative of f at C is the limit as h tends to 0 of f of c plus h minus f of c over h. So if we define this formally, the gradient function or derivative of the curve y equals f of x is written f dash of x or dy dx and is given by f dash of x equals lim as h tends to 0 f of x plus h minus f of x all over h. The gradient can be used to find the gradient for any value of x. Let's take a look at this notation. Lim h tends to 0 means the limit as h tends to 0. The expression cannot be evaluated when h equals 0, but as h becomes smaller, the expression approaches a fixed or limiting value. We will look at this in the context of differentiating sinx and cosx for small x. We begin by differentiating sinx and cosx from first principles. Let's recall the small angle approximations for sine and cos when angles are measured in radians. Here's a graph of y equals sin x and the line y equals x superimposed upon it. As you can see, close to 0, sin x is approximately equal to x. Let's now take a look at the graph of y equals cos x and the graph of y equals 1 minus a half x squared superimposed upon it. As you can see, close to 0, cos x is approximately equal to 1 minus a half x squared. We will use these two approximations when differentiating from first principles. Remember also that we will be using radians when differentiating trig functions. If we want to differentiate sin x close to 0, we let f of x equal sin x and x equals 0, and then apply this to our formula for f dash of x, as shown here. So we have f of x equals sin x and f dash of 0 equals lim h tending to 0 of f of 0 plus h, which is sin h, minus f of 0, which is 0 because sin 0 is 0, all over h. We will now work with lim h tending to 0, sin h minus 0 all over h. This is equal to h from the small angle approximation of sin x approximately equal to x over h, as shown here. And of course h over h is equal to 1, so the limit as h tends to 0 of 1 is equal to 1. Now let's differentiate cos x close to 0. We're going to again let f of x equal cos x and x equals 0. And so differentiating f of x equal to cos x gives us f dash of 0 equals the limit as h tends to 0 of f of 0 plus h, which is cos h, minus f of 0, which is cos 0, which is equal to 1, all over h. We're now going to work with lim h tending to 0, cos h minus 1 all over h. Using the small angle approximation, we have that cos h is equal to 1 minus a half h squared, as shown here. And then, of course, minus 1 remains as it is, and the h underneath remains as it is also. Tidying up gives us that this expression is equal to lim h tending to 0 minus a half h. And this is of course equal to 0. We will now apply these small angle approximations to an example. Pause the video and have a go. Press play when you're ready to view the solutions. Let's take a look at part A first. Assuming the small angle approximations shown, show that the derivative of sin x is cos x. So let's solve this. We're going to begin by letting f of x equal sin x, and then apply this to our formula for the derivative. So we have f of x plus h is sin x plus h, as shown. F of x is sin x, as shown. And h remains as it is in the formula. Using the angle formula for sine, we have that sine x plus h equals sine x cos h plus cos x sine h. Minus sine x is left as it is, as shown. And of course, h remains as it is also. We can now collect some of the terms together, as shown. So factoring out sine x in these two terms, we have cos h minus 1 all over h multiplied by sine x. And here we have sine h over h multiplied by cos x. As you can see, lim h tending to 0 cos h minus 1 all over h is equal to 0. Sine x remains as it is. Lim h tending to 0 sine h over h is equal to 1. And cos x stays as it is. Tidying up this expression gives us that this is equal to cos x. And therefore, the derivative of sine x is cos x. Now let's take a look at part B. Using the small angle approximations as shown, we are required to show that the derivative of cos x is minus sine x. So let's solve this. We let f of x equal cos x and then apply this to our formula for the gradient. So f of x plus h equals cos x plus h, and f of x equals cos x as shown, and h is left as it is. Using the angle formula for cos gives us that cos x plus h equals cos x cos h minus sin x sin h. The minus cos x at the end is left as it is, and the h in the denominator is left as it is also. Next we collect the terms as shown and factor out cos x to give us cos x times cos h minus 1 all over h minus sin h over h times sin x as shown. So we have cos x as it is in the formula. We have the limit as h tends to 0 of cos h minus 1 all over h is equal to 0. We have lim h tending to 0 sin h over h equal to 1 as shown. And we have sin x as it is in the formula. Tidying up this expression gives us that this is equal to minus sin x. And therefore, the derivative of cos x is minus sin x. We can also prove the more general results. If y equals sin kx, then dy dx equals k cos kx. And if y equals cos kx, then dy dx equals minus k sin kx. Pause the video and have a go at this example. Press play when you're ready to view the solutions. So let's take a look at part A first. We are required to find dy dx given that y equals sin 3x. So let's solve this. We have y equals sin 3x. And so, using k equals 3 in the standard result for sin kx, we have that dy dx equals 3 cos 3x. And now for part B. We are required to find dy dx given that y equals cos 8x. So let's solve this. We have y equals cos 8x, and so we can use k equals 8 in the standard result for cos kx to give us dy dx equals minus 8 sine 8x. And now for part C. We are required to find dy dx given that y equals 2 sine x plus 4 cos 5x. So let's solve this. We're going to solve this term by term. So for the first term, differentiating sine x gives us cos x, and therefore dy dx equals 2 cos x plus the differential of 4 cos 5x. And we work that out by applying k equals 5 to the formula for the differential of cos kx, as shown here, to give us the term 4 times minus 5 sine 5x as shown. And so tidying up gives us that dy dx equals 2 cos x minus 20 sine 5x. Now let's take a look at another example. Pause the video and have a go. Press play when you're ready to view the solutions. We are required to find the stationary points of the curve with equation y equals a half x minus sine 2x in the interval x greater than or equal to minus pi by 2 and less than or equal to pi by 2. So let's solve this. If we differentiate the expression for y, we have that dy dx equals a half, since differentiating a half x becomes a half, minus 2 cos 2x, since differentiating sine 2x gives us 2 cos 2x, with k equal to 2. At the stationary points, dy dx is equal to 0. And therefore, if we solve for x, the expression a half minus 2 cos 2x equals 0, we obtain cos 2x equals 1 over 4. As we can see from the cast diagram, cos is positive in the first and the fourth quadrants. So 2x equals 1.318 from our calculator in the first quadrant, as shown here. And so in the fourth quadrant, 2x equals minus 1.318. Therefore, x equals 0.659 or minus 0.659 in the interval x greater than or equal to minus pi by 2 and less than or equal to pi by 2. Now when x equals 0.659, we have that y is equal to minus 0.639. We've simply substituted the value of x into the formula for y to obtain this. When x equals minus 0.659, we have that y is equal to 0.639. And therefore, the stationary points of y equals a half x minus sine 2x in the interval x greater than or equal to minus pi by 2 and less than or equal to pi by 2 are 0.659, minus 0.639 and minus 0.659, 0.639. This brings us to the end of this session. If you have understood its contents, you should be able to differentiate trigonometric functions. Thank you very much for listening. To understand this topic in greater depth, do attempt the exercises in your textbook related to this topic.